a continuous current flow.
Yeah, we get a voltage divider, right?
Yes, you get a voltage divider effect. Sorry?
The DIO needs to have an optional 47k pull-up resistor, which should be enough so you can short to ground and get a decent signal out of the push button switch.
Yeah.
Okay, cool. And we're all good to go with the tape. So, hopefully the soldering iron is just about warmed up. What we're going to do is take these reed relays, wire them across the back of this appliance remote control. We'll load up some software that will let us pulse those outputs, and we'll see if we can control it. Actually, while I'm doing this, is there anybody that has the Arduino kits that is playing around with them and would like some quick assistance from Hugh or someone else to get things working?
There is.
We do have quite a few Arduino experts in the room, so if you need assistance, there are probably volunteers ready and willing and able. Okay, so what we have here is an Arduino with the reed relays wired across a couple of outputs, and the outputs from those are then wired across the buttons onto this appliance remote control. I'll stick the receiver in somewhere so that we can see it. I don't have anything to switch, unfortunately, but when the receiver turns on, this red light should come on. There will be some indication at least. Okay, so what we need next.
So you need both hands, right?
Thanks. Yes, was there a question?
Could you just move that water bottle, please?
This one?
Yeah.
Oh, yeah. Thanks, Marco. Great, thank you. Now this little program is very handy. It's basically something that I use a lot, or I use something based on this a lot when I am trying to put some kind of a software interface onto an appliance that doesn't already have it. Basically anything with buttons, you wire across it with one of these, you run the software on the Arduino, and you can then talk through the serial port and control the outputs. And essentially you can soft press the buttons. In this case, it's set up for 3 outputs, so output 1, 2, and 3 on pins 10, 11, and 12. What I usually have, just for mucking around and for prototyping at home, is a shield that I plug into the Arduino, so I do it a little bit more neatly than loose relays lying around the desk. A shield that I plug in that has a bunch of red relays and things on it already, so basically it gives me buffered outputs that I can talk to. In this case though, we're just using the raw relays, and we've only got 2 of them, so we don't really care about the first one. I've got this connected at the moment to pins 11 and 12, so it's outputs 2 and 3. All we're doing is setting up serial comms, specifying the outputs, and we're forcing the outputs low just as a bit of a setup thing to ensure that they start in a known state. And then we go into a loop. what we're doing here is looking for whether data is available on the serial port. So the Arduino itself is going to be sitting there watching the serial port, waiting for us to send things to it. And based on what we send, it will then do a different action. So if we send a value of 1, it means we want to pulse the first output. And what it does is do a digital write, so it sets the output on that one to high, waits for 500 milliseconds, so it's half a second, and sends it low again. So basically what happens is that by sending a value of 1 down the serial port, we cause it to send the output high for half a second and then drop again. So it's simulating a button press. And it has 3 outputs, so we can then control 3 different things. So in this case, I've got 2 relays wired up, so we can control 2 different things. So if I reset the Arduino and do an upload, we should be able to get this program running on the board. Okay, so after a couple of seconds, that will reset. Now we'll switch over to monitor mode. Now monitor mode allows us to also send values back down the serial port. And so I actually wasn't paying attention to which button I was wiring things to, but we'll take a guess. We'll send output 2. We'll see what happens. This is going to be another demo file, isn't it? Or output 3. Batteries in there. Does it work with that? No, the transmitter's not working at all. Ah, okay, it may be. Oh, damn. Hardware failure. Okay, that'll stop it. We just need to solder the power lead back on. I've got some wire cutters somewhere. You need to strip it. This poor hardware's been used for so many demos, it's falling apart. Do you want to try stripping it with this? Yes?
You can drive the camera?
Sorry?
Do you want to drive the camera?
No, that's fine. Thanks, Marco. Okay, so what we're also demonstrating here is serial communications. We saw earlier how to send values back down the serial port so that we could get feedback from the device and see what's happening. In this particular demo, we're also sending data to the serial port and having the Arduino respond on the basis of what we send it. Also, something I should point out, a really, really handy little program which I use all the time is a program called Ser2net, S-E-R-2net. How many people here have used it? Heard of it? It's very cool. What it does is allow you to, basically it acts as a bridge between the serial port and a network socket. And what you can do is define a serial port and a socket, and it will link the two together. And it allows you to expose a serial port to a network directly. What that means is that by connecting up an Arduino and then using Ser2net, at the moment we're using the IDE to talk to the serial port. It means that we could be exposing it over the network, which means that it's trivial to talk to it from basically any scripting language, because pretty much anything can make a TCP connection. So you could write some code in Perl or Python or Ruby or whatever you want to use, and you simply open a network socket, and you can be talking to the Arduino, which can then be interacting with hardware. So that's an example of a really cool way to bridge the gap between whatever your favourite software environment is and actual physical devices. Don't bother putting that on. Should be those two. Just see which one. No, that worked. Okay. So it worked when you press it. I'll try doing it out of software. Okay, cool. So if we send a value of 2, that's the equivalent of clicking the on button. And if we send a value of 3, that should turn it off. Hey, demo success. That wasn't that exciting. All right, so this is, as I mentioned earlier, this is a great way to isolate yourself. With what we've got here, basically a few lines of code, a couple of parts that we can buy for a total of about $6 down at JCar, and an appliance remote control, we could now be controlling physical devices from a network environment. So that's very, very cool. Analog input. I don't actually have a demo set up for this, but I'm sorry, did you have anything ready to go?
Nope.
Nope? Okay, I'll just explain what it is then. There are a variety of inputs and output ports on the Arduino, as Hugh mentioned earlier. Some of them are dedicated just to being digital I/O lines, and that's basically all they can be. You can read digital inputs, you can write digital outputs. There are 3 lines that are used for pulse width modulation, which we'll get to in just a second. And there are a number of lines that are available for analog input. And what this means is that you can read a voltage that might vary between 0 and 5 volts, and use that to, and you can take a value, basically you get a 1 byte value back from it. So you get a value between 0 and 255 depending on the voltage on the particular input. And that can be handy for a whole lot of things. So you can basically do things like connect a variable resistor and use it as like a volume control essentially, which can then affect things in software, so that'll control various levels and things. But I don't have a demo set up for that, so we won't demo that one live. 124? I thought it was 255. Okay. Yeah. Oh, okay, so it's a 10-bit converter. Yeah, I didn't realize it was that high resolution. Okay, excellent. So, one-wire introduction. There are a whole lot of little devices now that have some intelligence built into them, or they can communicate over a serial bus. And there are really 2 major technologies that are extremely similar. They work in a very similar way, but they're like parallel developments. One is one-wire, which was originally developed by Dallas Semiconductor, I think it was, quite a long time ago. It's a relatively old system. And they call it one-wire, but you actually need a couple of wires. They say it's one-wire because there's only one data line, but you still need a reference. So with a one-wire bus, what you can do is have multiple devices, each of which has its own ID, on a pair of wires, and then you can communicate with them individually. So there are some devices around that are actually quite cool that use this. Now personally, I find one wire to be really finicky. I don't know how successful other people have been with it. It's designed so that it can operate in what's called parasitic power mode, which means you really only need 2 wires. And the device itself basically powers itself by leeching power off the data line. And I've never really had much success with that. And I've also never really had much success with using it in a proper bus with multiple devices all connected onto the same system. Has anybody here played with one wire? How many people have been successful playing with multiple devices and all that sort of thing? Okay, a couple of people have had it working. Cool. What I usually end up doing, just because I don't like stuffing around with things that are fiddly, is run it in a powered mode where you need 3 wires. Basically you need a ground, a supply, and then a data line. So what I've got here is a whole bunch of little DS18B20 wired up to headers. So if anybody wants to play with these, I've got a few of them here and we can hand them out right now. Hugh, do you want to? I'll hang on to one for myself, but you can hand out some others. These are temperature sensors. Basically, it's a pre-calibrated temperature sensor that you can communicate with over the one-wire bus, and it will give you back values in Celsius, which you can then convert to whatever you like. So I'll connect this one up. For those of you that have boards, actually I've got a bit of an explanation of it here. So if you don't actually have your hands on it, that's what I have right here. It's in a TO220 package, so it basically looks like a transistor. It's got 3 leads, and it's just got a ground, data, and plus 5 volt inputs. And what I've got on these little assemblies is put them onto a header and put a 4K7 resistor, as a pull-up resistor, onto the data line. And let's get it working. We'll see how hot it is in here. Right, if you're wanting to plug these in, some of these I assembled with the resistor in the front, and some of them got the resistor in the back. But basically what needs to be done is plug it in so that the ground connection, which is the one with nothing connected to it, goes into the ground pin on the Arduino, and then it connects onto pins 13 and 12, which are the adjacent pins. So the data pin in this case goes into pin 13, connection 13, and then connection 12. is this? Thanks for pointing that out. Major oversight. If you want to play with this right now, there is a tiny little tarball, it's only a couple of K, that you can pull down from that URL. And that contains the example code that I'll show you now. I'll put this URL back up in a second, but just in the meantime, I'll show you the code. What we're doing here is defining that we're going to be talking to the one-wire device on pin 13, and we're cheating a little bit. What we're doing is using one of the I/O lines as a power connection. And that's just because I was wanting to put it onto a 3-pin header, and there was no ground input and plus 5 volts in a row, so I'm using one of the output lines as a power supply. So what we're doing is using, this is actually some example from a company called New Electronics in the UK. They're people that sell those little one-wire temperature sensors. They're also available in Australia, but I bought a few from a group in the UK. For reference, these little sensors in the UK sell for £2.50. In Australia, they're like $6, something like that. So they're pretty cool. And you can stick these at the end of a fairly long piece of wire. So you could distribute these around your house and have them in the ceiling cavity in different rooms around the house and things like that, and be logging data from a whole lot of different places. And that's basically the application that I have for them. So what we're doing is using, first we call in setup. We're saying that we want to take data from this input, and we're just setting this output high, so we use it as a power supply. Opening up some serial communications and saying hello. So once it's started up, it should print something to the serial port. It then goes into a little loop. And every 5 seconds, it reads a value by communicating using the one-wire protocol to the actual sensor itself. So let's just give this a go. So we should be uploading that to the board. And once it finishes, so switch over to monitoring mode. So we're now watching what's on the serial port. And once it finishes its little boot up cycle, we should get the hello. Yep. So it says, hello, I am a temperature sensor. One of the little quirks about these particular Dallas chips is that they always report 85.00 degrees the first time. Basically, it's like saying, hey, I'm here. But you have to ignore the first value if you're reading it on, immediately after startup. So what we've got there is a read every 5 seconds, and it's currently around 28.18 degrees. So Hugh's putting his finger on it to try to make it get a bit hotter. Oh, sorry, it's a bit hard to read on that screen there, isn't there? 29.31. No. We can hold it nearby. You probably have a bit of radiant heat from it, and we'll see what happens. Just hold it right near it. Yeah, we'll see if we can sweat it up a bit.
What's the upper temperature limit for
I don't know, actually. I think it might be 85 degrees. Yeah. They don't have an enormous range. Like, you wouldn't want to use these for measuring boiling water and things like that. They're really just for ambient temperature sort of range. I'm not sure how far they go negative, but I don't think it's very far. I think it's like... Sorry? Yeah, RTF data sheet, which is actually on my computer, but we'll move on. Yeah, so as you can see, it was responding to the heat that it was picking up from the soldering iron there. And they respond quite fast. Like, if you grab one in your fingers, a couple of seconds later, you'll see the temperature change. Yes? I'll just switch back to that diagram. So you can't really tell from that picture, but the orientation on the TO220 package is with the flat face towards you at that point, so it curves around behind for those of you that know the shape of a transistor package. Yep, so the comment was that you can attach a heatsink or some form of thermal transfer onto the device itself so that you can get faster response times and things like that. So, yes? 0 degrees? Damn. Just have a quick look at that. So, resistor goes towards the right and that's ground. You just make sure it's plugged in the right one. Actually, how about you just take this with you? Okay, Hugh's just going to have a quick look at those ones that aren't working properly. Yes?
Other than the one-wire data chaining and the parasite power stuff, would you say there are any advantages to the AS8 differently other than that you don't get with an analog sense like now?
Probably, well, the theoretical advantage of the one-wire stuff is that you can run a single pair through through a large area and have a whole lot of multi-drop system basically. So you don't have to run an individual line to each one. So that's the major advantage of using a sensor that uses a built-in communications protocol rather than simply outputting a value to you. I think cable run is also an issue as well. You probably wouldn't be able to go too far to a direct analog sensor. I'm not sure what the limit is on one wire, but it's reasonably long. Like you can run stuff around a house without any problem at all, just on twisted pair. A few hundred metres, and you can use relays and bridges, is the answer from Julian. Repeaters and bridges, yeah. Was there another question? I saw a hand. Yes, Bob. Sorry, what was that? Okay. Yeah, this is what I was referring to earlier about multi-drop and having multiple devices. In the one-wire protocol, you have a device identifier. So you can have multiple devices and you can say, I want to address just that particular device and get a value back from it. I'm basically being lazy and I'm running an individual cable to each one and I'm just addressing whatever responds on that. That's basically because I've had problems with trying to get multi-drop working, but in theory it supports device IDs. And people smarter than me, I'm sure, have got it working without a problem at all. Okay, so we'll have a quick look at the Wii Nunchuck introduction. So the other very similar technology is I2C or I2C, people call it different things. This is, once again, a very simple multi-drop communication system, which is, it basically works in the same way as one wire, is what it comes down to, but it's a parallel development. It can do higher data rates, longer runs. It's got a couple of advantages to it, and it's being used in quite a lot of devices now. So the Wii controllers are I2C devices. So there's a Wii Nunchuck that I have here, which is an I2C device. So what we can do is use a library that's been developed for the Arduino to talk to I2C devices and read values from them. So in this particular case, these devices have accelerometers in them, which is very, very cool. And they're really cheap. I think these are like in the order of 20 bucks or something, aren't they? I haven't actually bought one. I took someone else's and cut the end off it. But I think these are only about $20. So for 20 bucks, you can get yourself an accelerometer that you can connect up to an Arduino and talk to very easily, which can be really handy for a lot of robotics projects or measurement projects. So what we'll do is connect this up to...
We've hit the demo gods have been a little unkind to us with the, for those of you that are trying to get the Dallas one-wire sensors going, the newer boards have a LED across the same pin we're trying to read the data in off, so we'll need to rejig that circuit for it to suit those boards. So if you're getting zeros, you haven't done anything wrong, it's just because there's a LED on that pin, it's not able to actually access the device. So we'll have to, we'll work out some way of, we'll send a patch, basically.
Sorry, that's my fault for using old technology. Unfortunately, you probably can't see it too clearly, but what I have here are the 4 wires coming out of the end of the Nunchuck controller. Basically, it's a couple of power lines and a couple of communications lines. So what I've done is connected it up to ground and plus 5 volts, and at the other end, I've connected it to a couple of the I/O lines. And I also have piggybacked off here another little connector. There's a header here, which will connect up to a servo. So this is going to be a bit of a double demo, so twice the things to go wrong. And we're going to use one of the digital lines, one of the PWM lines to control the servo based on the accelerometer input that we're going to read off the Nunchuck itself. So over here, somewhere we have a servo. For those of you that haven't seen these things, these are very, very cool little devices. Basically, it's a box with a little knurled knob sticking out of it, to which you can connect a variety of different things, like little discs with slots in it and arms. These are really cool if you want to do direct control of physical devices, so if you want mechanical control of something. And they come in a wide variety of sizes. This one's a relatively small one. It's typically the sort of thing you would find in a remote control car or a radio controlled aeroplane or something like that. But you can get them up to very large sizes with huge amounts of torque. And we'll get to PWM in a moment. I'll explain that later. But basically you can control the position of the arm. It's not like a motor that simply spins when you apply power. It's an actuator where you can specify the position that you want to move that to. So what I'll do is connect that up as well. That's right, this one's quite a small one, so it doesn't really take very much. Not yet. I'll just the lights are busted.
They're busted. They're busted.
I'm looking for...
No, I know. I was just trying to get rid of the shadow. It's not making much difference.
Okay, so this is an example that I actually just grabbed off someone's blog. And it's a project, as I said, to read a value from an accelerometer that's inside the nunchuck and then control the position of a servo motor. And it's relatively straightforward. Basically, we're just specifying, once again, what pins we want to use for what purpose. Servo pin, pin 7. That does not sound right because pin 7 is not a PWM. Oh well, we'll see what happens. Oh, it's probably just doing a square wave thing. Okay, so what we're doing is, in a little loop, we're reading the accelerometer value from the nunchuck, and then sending different values. What have we got here? Pulse width. Yep. So we're sending a variable pulse width to the servo. And there's some... Sorry? The patch for the DS. That would be handy. You could email it to me, that'd be great. And there's some other stuff that it's using to read the various values and also send values back to the serial port so we can see what's going on. So let's give this a try. I'm skeptical. I had this working, but I'm looking at it now, I'm not quite sure why it was working. Well, it is working. That's actually quite surprising. Okay, so what we have... Oh, thanks, Hugh. Yeah, we'll give it a shot with the camera. Okay, so you can see the little servo motor that's located just there. And then if I pick up this nunchuck and move it around, as I move it, the servo is moving. So it's reading values, and if we were back in the other screen, where it's got values being spat back out at us, you can see that 183, 180, and as I move the controller down, 169, 168, 150, 141, etc., we're getting different values. So this is a really simple way to get direct feedback for all sorts of things, all sorts of projects. So I personally think that's pretty cool. I like that. Which gets on to PWM. Now, there are 3 outputs on a typical Arduino that are designed for PWM output. And I'll just give you a very brief explanation of what this is. basically a way of simulating analog output. With true analog output, you have a pin that has a varying voltage. And you might have, say you want to have it at 50% level, you might have an output pin at 2.5 volts out of a 0 to 5 volt range. Digital devices are really, really bad at doing analog work. And so pulse width modulation is a way of simulating an analog output, or sending a signal that says, I want this proportion of the output to be on. And it does it by basically having a square wave. And you can see in this particular diagram, the blue line, the V line, is the actual voltage. The scale on this is obviously a bit odd, but basically it's a logical 0 or a logical 1. And so the output can be either off or on. And by varying the time that it's on, you can vary the representation of the value between totally off and totally on. So it's a way of faking analog output. Servo Motors talk PWM natively. So they will understand that pulse train, and they will move themselves to a position proportional based on, between the two limits, based on the value that you're sending them. So we've already done a bit of playing around with the servo, so we won't go into that in more detail. But basically, if you want to talk to servos, the Arduino can do it natively. As was mentioned, someone down the front here pointed out earlier, this must be pulling a very small amount of current, and it is. It's a very small servo. If you're dealing with larger servos, you'll probably need electrical buffering in there. But the actual signal that it's going through is the same. It's the exact same principle. Did you want to mention anything more about stuff? Okay, Ethernet shields. Now, I have a bunch of Ethernet shields here. Unfortunately, demonstrating this stuff is actually really hard in this environment. We'd have to build ourselves a little network, and we're not really all set up for that. But what we'll do is show you a couple of the available Ethernet shields and talk about some of the limitations of it. There's two. For a long time, people have been saying, Arduino is really cool, but I don't want to just talk to it through USB. I want to stick it actually on a TCP/IP network and be able to communicate with it directly and run web servers in them and things like that. And it took a little while, but a number of companies have come up with solutions. And the other thing that really sucks is they're expensive. But there are a number of solutions, like this particular one, which is a new electronics board, which came from the UK, same place I got the temperature sensors. And they are implemented with varying degrees of crappiness, mainly towards the more rather than less end of the scale. But there are some extreme limitations that are being dealt with in trying to implement this sort of thing. The big problem is that a TCP/IP stack is actually reasonably complicated. And so the library that is supplied, for example, with this new electronics board allows you to do things like open a network connection, but it can't handle multiple packets. So if you want to do something like run a little HTTP server, which you can do out of using one of these, in fact I've done it, you can even run a little CGI thing so you can send values to it, you have to make sure that your entire response fits within a single packet. So there are certain limitations you have to work with. You can't exactly use proper compliant HTML and CSS and all that sort of stuff because you just don't have room for it. But if you want to implement some very basic TCP/IP connectivity, this is pretty cool. You can do things like set up very simple web services where you want to check the value of, say, a temperature sensor that might be connected to one of these boards. You could run a little piece of software in it which basically provides an HTTP server, and when you connect to it, it responds with a page that includes the value of the temperature sensor. So you could do a little very crude ghetto web services type system. And similarly, it can read parameters that have been sent to it. So you can use a form or a push button, like a button on a web page to click on to then control things connected to physical outputs. Yes?
Do any of them support power over Ethernet?
Not yet is the answer. Yeah, you can fake it using a breakout. Using a breakout connector that plugs into the Arduino board. That's what quite a lot of people do. That's a pretty common approach. So the question was, does it support power over Ethernet? Yes? What's the range of costs? Okay. Typically around the $60-ish mark. It varies depending on the manufacturer. I'll show you a couple of different types. There's which one's this one? there's a WizNet.
That's actually slightly different, Alice. I might come to that.
Okay. Hugh will elaborate on that one in a moment. The new electronics board is the one that I've played with personally, so that's the one I know most about. That's the blue one. There's this other one that Hugh has here. Do you want to talk about these other ones?
Yeah, so the second board there, the white one, is actually electrically the same board as the Arduino, the new electronics one. It uses the PIC or the microchip PIC. A microchip Ethernet controller, and it has the same has the same limitations as the blue board. The one I got there, the white board beneath, that's one I arrived like 2 days ago, which I bought over eBay, and it was about $30. So it came from Hong Kong, so it was a bit cheaper, but electrically the same thing. The other board I wanted to point out is the just juggle these around. This little red board actually takes quite a different approach. This uses a part made by a Korean company called WizNet, and the approach they've taken is actually a little bit different. They actually do the entire TCP IP stack within the chip, and basically what you're presented with from a programming standpoint is a set of socket interfaces. So you have in a sense a command channel. So over the command channel you set your MAC address and your TCP IP address for the host, broadcast, and some of those basic sort of parameters. And then there's the WizNet chip itself has all the Ethernet framing hardware, but also has a little microcontroller that actually runs the stack. The main advantage with that, of course, then is that from a software standpoint, on the Arduino side, you don't have to run the TCP IP stack on the Arduino, so you're saving code space and I guess some complexity and compute power. The downside is you don't have quite as flexible an interface. You basically just have a socket style interface, so that you can't sniff arbitrary Ethernet packets if that was something you're wanting to do. These little boards you can actually buy online from WizNet directly, and the slides that John and I put together have the name which Google will turn up for you. They're about $15 to $20. They're actually quite cheap. And I bought a whole bunch of them which I never actually got around to using a project, so if we can find some creative way to do it, we've got a couple which we'll chuck into the audience later if people want to play around with that.
Cool. Export, yeah. I don't think we have one here, but there is another supplier. There's another version called an export. Or maybe Hugh does. We shall see. Father Christmas going into his stack. In the meantime, hey, we're out of this. Ethernet shield. Yep. Yeah, export. So these are the a couple of the models. The one that's not listed on there is the new electronics board, which is the one I've got here. Now we're pretty much at the end of the demos and the building blocks that we have. We have about another 15 minutes or so. I know that there are a couple of other people here that have got some really cool hardware that show some of the other applications. So the Arduino project. Who was it? Was it Josh who had the Arduino? Do you have it here by any chance? Excellent. Would you mind bringing it down just so that we can show you some of the things that can be achieved with this? He can probably give a better explanation, but my understanding is that the Arduino project is an attempt to build a Rally computer that's entirely open source, so it's based on an Arduino. It takes an input off a Hall effect sensor, which it picks up wheel rotation and measures distance over ground, and it has a whole number of things that it can do. So it's connected to a nunchuck for control, and I don't think you're using the accelerometers, are you? Just using the... Yep.